Our next speaker will be Khanh from Ohio Wesleyan. He's been working with Craig Jackson this summer. And the title of his talk is Specializations of the Lawrence Representations of the Braid Groups at Roots of Unity. Welcome, Khanh. Sorry, everybody.
My name is Khanh, and this summer I work with Dr. Craig Jackson on the specialization of the Lawrence representation of braid groups at roots of unities. And here are some concepts that related to the topic. First of all, what is a group? So a group is basically can be thought as a generalization of the number system with a set that contains elements behaving like numbers and a binary operation that behaves like multiplication. For example, the set of all invertible linear transformations in n-dimensional space and the operation composition of transformation forms a group. And since linear transformation can be represented as matrices, so this group is completely equivalent with the group of invertible matrices of size n by n. So what is a braid group? So a braid group was first introduced by Emil Artin in 1925. Since then, it has appeared in many different branches of math and physics. And here's a really nice geometrical interpretation of it. Imagine that you have a disk with endpoints, and on each of these points you have an ant. And these ants will play the following special edition of the musical chairs. So when the music starts playing, the ants will start moving around on the disc. And when the music stops, the ants will come back to the starting points, but not necessarily their original starting points. And since this is a special edition, we're going to be nice to them and we won't remove any points at all. And if we plot the path with the time being on the path of these ants, with the time being on the vertical axis, what we obtain is a braid element in the braid group B sub n. And here we don't distinguish braid elements that we can obtain from one or another by pulling, stretching, or shrinking the path with just the exception of cutting them. And the braid group composition is simply having these ants playing 2 rounds of musical chairs. And we can in fact check that this is a group. And also we can realize that these groups have infinite number of elements, since there are infinite number of ways that the path can wind around each other. However, Emil Artin has shown that we can actually define this group in terms of a finite number of generators, sigma 1 through sigma n minus 1 that's shown right here, and the following 2 relations. What that means is the study of braid group can be broken down to study these finite number of generators. Another interpretation of braid group comes from the realization that braid group can be realized as a form of mapping of a unit disk with n puncture onto itself, such that the mapping fixes the boundary. And to describe this group, we don't really have to describe all elements of them, and we just need to describe n-1 elements according to the earlier definition. And those mapping corresponding to the sigma i's are called the daintwist. So the daintwists are the mapping on a unit disk with n puncture in such a way that the daintwists corresponding to sigma I are the one that lift the I and I plus first punctures up and map them in such a way that's the same as rotating these punctures around each other in the clockwise direction at 180 degrees. And as we can see, these such a mapping fixes the boundary, and also we can show that this mapping satisfies the two relations given earlier. So they in fact corresponded to the finite, the generators of break group. What we interested in about break group is a representation of them. And so a representation is a correspondence between an abstract group G and a group of matrices, such that the correspondence behaves nicely with respect to the multiplication in the abstract group and the multiplication within the group of matrices. And many ways to construct a representation is to let the abstract group act on some space, and we can associate that space with a vector space. For example, we can figure out the rotation through the matrix corresponding to the rotation through about an origin with the angle of like 90 degrees by associate two unit vectors on a plane and calculate how the rotation acts on those vectors. And in the same manner, Ruth Lawrence has associated the vector space H of n comma L, with L being positive integer, to a unit disk with n punctures to create a family of Lorentz representation for these break groups. And this vector space has coefficient in the ring of polynomials that has integer coefficient and also allows for negative power. And elements in this vector space basically are the standard force and the linear combination of these standard forces. And here's the form of the standard force, which basically consists of some strands only connecting adjacent punctures. And the total number of strands must be equal to L, and there's handles coming down from these strands in the order from left to right and from top to bottom. So the question is, how can break group act on this vector space? And so break group has a natural action on vector space via the dangers I shown earlier. So for example, in H of n, 2, we have the break group action on this standard fork by twisting this I and I plus first puncture in a clockwise direction, and the strand just come along for the ride. And we can actually break this fork down into similar simpler forks. And we also have rules that turn these forks into a standard fork. And these rules are, if we want to pass a handle through a puncture, it costs us a factor of Q. And if we want to pass a handle through a handle, then it costs us a factor of T. And if we introduce the following notation, f of I minus 1 being this standard fork with all this all L strand connecting the I minus first and the I puncture, then in H of n2, the previous computation becomes a nice equation like this. And one of the results concerning the Lorentz representation is that the first members of the Lorentz representation is the famous Barral representation. And we can show it by simply compute the action of sigma I on the standard forks from f sub j. And by identify the fork basis with standard basic vector, we have the following matrix representation for sigma sub I, with I being the identity matrix. And so why do we care about specialization at roots of unity? Well, we have the following observation. If we consider a subspace in H of n, 2 spanned by these following vectors, then we can do the following calculation. And even though these forks lie outside of our subspace, if we substitute t equal to -1, which is the root of t squared equal to 1, Then this term 0, and we have a minus right here. And if we put them in a matrix form, we obtain the following matrix, and this is the Barra representation if we identify q squared as q. So we make a conjecture that can we generalize this pattern for any n. And indeed, we have proven the result that there's always a subrepresentation isomorphic to the Barra representation for any n and l. And here's the identification. And we also have proven that there's no complementary subrepresentation for any n larger or equal to 4. However, for n equals to 3, we can have a complementary subrepresentation under the additional specialization q equal to t. So what I would like to investigate further is to have a description of the quotient representation and to see if there's a relationship between our specialization and the specialization in the paper by Jackson and Curler, which also has similar results. So at the end, I would like to thank the Department of Math and Computer Science at Ohio Wesleyan, OU Summer Science Research Program, NSSF and RU, and Dr. Jackson for guiding me through this research project.
Okay, thank you, Khanh. Questions?
I'm sorry, but could you explain what a root of unity is again? Or what would it look like geometrically?
So root of unity here is, a complex root of unity, which are numbers that satisfy equation t to the n equal to 1. And since it's a complex root, they lie on a unit circle in a complex plane.
I liked your example on the ants and the musical chairs. But I was wondering, what kind of applications are there to, can braid groups be used in other fields as well? Or is it just like a pure mathematical concept?
Well, I've heard it. I've read and noticed it has some application in some branches of physics and some branches like pure math, but I'm not entirely sure what they are and how can they be applied.
Any other questions? Okay, let's thank Khanh again.